Yeah, thank you. Good afternoon. My name is Adedeji Victoria from NLC, and I'm grateful for the opportunity to give this presentation on one of our ongoing projects and see a few things to check along the way. On probably last structure on page one, exit cross correlation. And my outline would be to say a few things about the H1 and the TSE, to show some previous constraints, what we've done in theoretical forecast, and what we're hoping to do next. Yeah, the 21 centimeter line is becoming a powerful pro of cosmology, heading reverse and interstellar medium. And because hydrogen is an organ, it's distinguishable from other emission lines, and the observed frequency gives us a good measurement of redshift of emission, and the number of observations are ongoing to help us to gain more information about the ancient system. This in principle help us to study first stars, galaxy, process of realization, which marks the end of the cosmic dark ages, studying the universe and the redshift. And because the neutral hydrogen also shows the distribution of matter, we would probably use that to study galaxy evolution and clustering and formation of structure. The TSE on the other is the inverse quantity scattering of the CMB photons coming from the surface of last scatter of the fourth ionized electrons in galaxy cluster, and is sensitive to the electron temperature and density. And by studying the TSE, we can actually gain understanding of distribution and property of hot ionized gas in the clusters. And TSE has become, it's a powerful probe of cosmology. A number of literature justifies this. And one of the things we've done before is to combine the TSE probe with the ISW to answer the question of whether gas is correlated on large scales and to probe the missing variants. We've also combined that probe with projected galaxy density reconstructed from data using the WISE or Sky catalog to probe galaxy properties and hydrostatic mass bias parameter, which is informative to help us to see if there can be a reconciliation on the estimation of SA coming from CMB and cluster kind of experiment. Similarly, in 2018, Bullet combined constraint from the TSE angular power spectrum with the parameter scalar amplitude constraint by CMB data and H0 to place type constraint on W. So the TSE is also versatile, an integration over line of sight. And why do we want to cross-correlate this with the H1 and what do we hope to get? At the end of this talk, I'll be able to show you what we have been able to do with this theoretical forecast in a way which is still ongoing to place constraint on the error of the neutral hydrogen fraction. Before this, the cross correlation is something we should expect. We expect exit to correlate with H1 on large scales because SE is sensitive to the hot gas in galaxy clusters, and this traces the underlying matter. And H1 also, all H1 in the post-realization are all in galaxies, and it traces the matter density on large scale shaped by gravity. Therefore, this correlation on large scale should be possible. I'll show you a few of what people have done before, placing a constraint on the neutral hydrogen fraction. The neutral hydrogen, the measurement of neutral hydrogen, particularly on low redshift, can be obtained by calculating all the gas in galaxy, basically by trying to determine the actual mass fraction, which is similar to the stellar mass function. But in this case, focusing on the H1 specifically. And other methods have also been used to make an estimate of the omega H1, methods like the H1 spectral stacking, the early observation. also been able to say something about an aligned 21 centimeter signal by cross-correlating H1 with data, school data, and so on, and place a constraint on the joint product of the neutral hydrogen fraction, the bias parameter, and the galaxy hydrogen correlation factor. But with a more sophisticated model, one may in principle be able to calculate BH1 and then put an independent constraint on omega H1. This is particularly what we're interested in, so put a constraint on the error of omega H1 using this possible cross-correlation between H1 and the TSZ. Yeah. Now for the theoretical forecast, we use the Hilo model to describe the H1, and one can in principle look at two approaches. One is to describe the H1 distributor within each dark matter Hilo following the density profile, more like taking an average of all the H1 harmonic galaxies, and then you in principle describe and then calculate angular fast spectrum which encodes the astrophysics of the H1. Another way is to use the HOD, which has been done extensively, particularly when you're interested to describe the discrete galaxies, within the Hilo. But for the purpose of this work, we decide to use the first approach, looking at the scales that we're actually interested in. And the HOD will be probably more relevant if you want to go into more smaller scales. And so if we assume a density profile, we can write down the Fourier transform of the normalized H1 density profile, and then calculate the 2D H1 temperature gravitational field. In parallel, we can as well write down the 2D TSZ field, plug that into the expression for the 1 kiloton and 2 kiloton of the Hilo model. And there is something to see. Of course, we expect the 7 kiloton to follow the dark matter power spectrum. As it rapidly decays, as we see, and then the cosmic variance dominates large scale, and then the 1 kiloton begins to dominate for about greater than equal to 20. And looking at the redshift dependence or the mass dependence of this probe, the TSZ optoangular power spectrum indeed is sensitive to relatively low redshift and high mass objects. And this would probably, at this multiple, correlate better with the fast H1, which is coming from that redshift window of 0 to 0.35. And we can as well see from the mass dependence of H1 and H1y, in this case, cross correlation that's sensitive to a wide range of objects, including classes from different masses. You may want to also pass in this theoretical forecast, how would you take into account RFI and etc. In the real simulations, what one would do is to first of all identify the frequency range that is dominated with RFI, and then do some flagging and masking, and use the clean data to estimate the power spectrum. So in this case, we just transform the frequency to a redshift that corresponds to this frequency. I will call that out of the power spectrum, so in a way it's more like maxing out this redshift range from the power spectrum calculation. And then we compute the power spectrum in that I showed previously. For the foreground, one may in principle want to adopt some foreground model to be able to do this, probably incorporate that into the Hilo model. But if indeed we know that we don't expect the foreground coming from Milky Way to correlate with TSZ field, and previous literature justify the 21 centimeter with the H1 field with CMB lensing is more robust against foreground. The CMB lensing is also an integration on the line of sight, like the TSZ. The foreground may probably not impact the cross correlation too much, maybe at this level of theoretical forecast. Where for simulation, what we should think about doing this more properly. And so we didn't consider the foreground. And the noise, using the noise term, one can basically compute the cosmic variance, and you may want to also model the fast noise as a Gaussian white noise. And so if we do such a theoretical forecast to place an error on the omega H1, of course, probably something that you're expecting to see, you are not disappointed. The error is actually very small on the omega H1, and this may probably be because of the assumed sky coverage that we use, or the long exhibition time that we adopt for this. So we said other parameters as astrophysical parameters are sensitive with YY also power spectrum. We may as well want to expand the parameter space by including by aligning other parameters from the MH1 to be free, and then we place a constraint on them to see how the correlation with other parameter appears. And indeed, this theoretical forecast proves that this kind of cross correlation on large scale is useful to place a constraint on the error, of course, on the omega H1. And one, we want to take this forward, like I said, an ongoing project to test this with simulation and include other foreground, RFI, and relevant parameters to be able to deal with the systematics. And probably one thing that one may also want to look at is if we square the H1 and cross-correlate it with the TSE, would that help us to test the correlation at small scales, where probably one would expect that the more you try it, you will have the less ionized gas there should be. And yeah, this is what we've got so far. Thanks.
Thank you very much. Questions? Okay, I start. So you have a very naive one. So just help with my intuition. So typically in my mind, I associate H1 with cold gas and TSE effect with warm. So could it be that there is more scale we actually see an anti-correlation between the two signals?
That's a sensitive question and very interesting indeed on small scales. Yes, one should probably, they will probably be anti-correlated. But yeah, we could also probably see some indirect correlation. On small scale, we have to do the simulations to eventually know, but yeah, in principle, it should be anti-correlated. But if you want to imagine that H1 rich galaxies are found in the same clusters of TSE emitting ionized gas, probably there should be some indirect correlations that we see. But yes, this is something we test and check.
Thank you.
Should we be also worried about in cross correlation about the galaxy bias and also cross correlation coefficient? I don't see those analysis in your current future forecast. Will that be an issue?
Yes. So for the H1, H1 bias parameter and the galaxy hydrogen correlation correction. So in this theoretical forecast, we did not include the hydrogen galaxy correlation correction. But I didn't show that here, but in principle, one can use it there to calculate the H1.
Any other quick question? Okay, if not, let's thank our speaker.